so we're just going to go through and take a look at this packet that you had to do in class today. And my expectation was actually that you got this thing done. If you're not focused, you're not going to get it done. But if you're just working 100% and really working with almost a kind of desperation to get the thing done, and I only see this kind of happen on exams, but if you work like that every day, it's kind of a good way to work in this class. It's just really work hard, work fast, and like it's like practicing sports. We seem to have this thing where it's okay to give hard in sports, but somehow in academics it doesn't have to be that way, and I fundamentally disagree. So we're going to actually kind of go at a pretty quick clip here. So if you get a little lost, you need to stop the video, rewind, watch again, and talk to other people and me. So we want to know what the y component of the we want to know what is the y component of the acceleration of the object, and when is it the least, when is it the greatest in the situation. Well, this is actually a trick question, and I love this question. I'm going to put a star here because you're going to see all kinds of variants on the exam, and I want to be very clear here. The acceleration on this object is g, which is negative 9.8 meters per second squared. And I want to be clear, it is always g. It is always g. Okay. It's never least or greatest, because you always have gravity acting on the object in the y direction. So in the y direction, the y component is always 9.8 meters per second squared. It's always downwards no matter what the object is doing. That's what you've been doing with these whole labs, is realizing, hey, there's only one kind of acceleration. It's just gravity. It's downwards. And what this does is this answers number 2 for us. The x component, so this is a in the y direction. A in the x direction, it's just going to be 0 meters per second squared. So this is also a trick question. There's nothing happening in x. So the acceleration of the x is always 0. So if they asked you like a third question, like what's the acceleration, and they didn't tell you a component, you would say the acceleration is always 9.8 meters per second squared, or negative 9.8 meters per second squared. The acceleration is gravity, and it's downwards. Now, when is the y component of the object's velocity the greatest? So that actually happens at the bottom. So here and here. The reason is that as you travel up, gravity slows you down in the y direction. You stop, you turn around and land. So the way you would say this is at the bottom. And here when we say what is the y component, I know some of you will say, well, it's negative v naught y down here. We actually proved that in class, that we have v naught y when we start and negative v naught y at the bottom. And it's the least at the top. It's the greatest. So it's at the bottom it's the greatest. At the top it's the least. And this is because gravity hasn't slowed it down yet. And here it's the least because gravity brings it to stop at the top in the y direction. It's still moving in the x, but in the y direction this actually comes to a stop. So actually Vy at the top equals 0. Vy naught at the bottom is going to be V naught sine, if you look at this picture, V naught sine phi. I'm giving you a little extra information here. Now, when is the x component of this velocity greatest? Well, V naught x is always going to be V naught cosine theta, and this never changes. And again, for that, just see number 2 that we did just now. That'll tell you why. Now, when is the speed the greatest? The speed is the greatest at the bottom. And I mean here, and so here, it goes through the air, and here. So what's actually happening at the bottom is because we have the max Vy at the bottom. Okay. And by the way, this speed happens to be V naught. So you actually have some interesting things. So a really good exercise for you to do is to say, well, what's the velocity here, here, and here? Like at the bottom. What are the components of the velocity? That'd be a really neat thing for you to kind of solve. And what are the components of the acceleration? So there we go. Now, question number 6. This is one that we actually kind of did in class. and I'm going to actually just go through this and get it done. And I actually had one more part to it, which is I want to know the height the ball goes. So we're going to be using all of our equations to get this one. So again, you're expected to remember these. So you're expected to remember that the height is v naught squared sine squared theta over 2g. You're expected to remember that the horizontal range is going to be v naught squared sine of 2 theta over g, and that the hang time is v naught sine theta over g, and you times that by 2. So you're expected to memorize all these formulas. So that's something that we're going to actually be using a lot. So let's go ahead and take a look at this problem now. So we want to find the x and y components of the velocity. So we have a speed, we have an angle of 5 degrees, and we're going at 15 meters per second. And let's go find the x and y components of velocity. And again, since we're talking about initial velocity, I know you're very tempted to use r as your letter. Don't use r. Use v naught x and v naught y to distinguish these things. So this is going to be 15 times the sine of 5 degrees, and this will be 15 times the cosine of 5 degrees. So we'll actually go ahead and calculate these values right now. And in the cosine, that'll work out to be 14.94, and in the y direction, we'll actually end up getting 1.31. And again, these are meters per second. Now, this actually ends up being irrelevant, though, when we have these formulas here. So, for example, let's just find the total hang time of the ball in the air. Well, I'm just going to use the hang time formula. So t is 2 times 15 times the sine of 5 degrees divided by g, which is 9.8. So actually, it's not so irrelevant because we got this right here. So we're going to say 2 times 1.31, plugging in from here, divided by 9.8, and this ends up being 2.62 divided by 9.8, so we'll get the time for that. And we end up getting a time of 0.267 seconds total. Now we want to know the distance the ball travels down the field, so we'll use x equals v naught squared sine of 2 times, and all this goes in brackets, 2 times theta, theta being 5 degrees, divided by g. So this ends up being 15 squared times the sine of 10 degrees divided by 9.8. And we're actually going to get our range from that formula, and we'll end up getting for our answer 3.99 meters. Excellent. Now let's get the height. To get the height, I'm going to call it h, but I'm going to use the y formula here, which is this guy right here. So that ends up being v naught squared sine squared theta over 2g. And of course, v naught sine theta, well, that's what we got here. So that's 1.31 quantity squared divided by 2 times 9.8. You got to be careful how you put these things in your calculator. And you end up getting 0.088 meters, so about 8 centimeters high. That makes sense given the angle it was fired at. So that's the answer to that problem. Now, here we have a wonderful question, and this is why I actually had you create a table for this. So here's what we're going to do. Let's just go ahead and set up our table here. And wow, look at this. All this wonderful stuff. And you know what? I'm just going to say we've got v naught, we've got theta. Let's see, we want initial velocity. And so angle. Okay, let's do it their way. So they want angle, then initial velocity, hang time. Distance, and actually I wanted that to be range, and I'm going to need to change this. So you should actually have something else written on your sheet. You should actually have height, and instead of seeing the word distance, you should see the word horizontal distance. So I apologize for that typo on mine. Yours should already be corrected, and height. So we'll actually go ahead and solve for these, and we'll take that up in our next video as we use Excel.